Hello everyone, welcome to the second problem session of this week. Today I'm going to do this problem. This question number 2 from JEE Advanced Paper 1. So this is an interesting problem in scattering or collision. Okay, so this thing that you see the word here, scattering, same thing as collision. So a particle of mass equal to 2 times m. M is another particle at rest. So this is like m1 and this is m2. Now after collision, this m1 goes that way and m2 goes this way. You might say, let's give a name phi, but when you read the problem, it's all about this angle theta. So you might not need any of this, we can also label this guy has a velocity v1 initially, not given. This was initially v2 is 0. And then after the collision, let's call it v1 prime vector. We don't know what the size of that is, what direction it is. And let's call this v2 prime. Okay. So this is, when you look at it this way, this is to find this angle theta is the problem. Okay, and you're not supposed to find the angle theta itself, just supposed to find maximum that this angle will be. And the collision is elastic. If you may have done some problem like this with like a smaller mass here and larger mass there, and if this guy hit infinitely massive mass, it's going to come back. It goes in there and come back like that. So if that was the case, so if the particle went in and then reflected back, so this original, this next is this original direction, this will be pi, if that was the case. And that will be the case if it was elastic and it was infinite walls, for instance. And you might remember that answer and just say, oh, I'm going to just do pi. But that turns out to be wrong. Okay, so we really have to actually do this problem. All right, so this problem and problems like this, when you have two-dimensional collision, often it's really helpful to kind of go over into center of mass frame. So what's center of mass frame? So center of mass, so this is my original situation, right? This is the original situation and this is the final situation, right? It's initial, final. So if you look at center of mass of these two particles, it's going to be somewhere here, just a point in space, center of mass. And that center of mass, because this is moving, it's in this frame, center of mass will go with a velocity of center of mass. And you can figure that out. So VCM, you can say this is all x direction, so all going to be x. So VCM vector just will be VCM I hat in this coordinate system, and so the VCM will be mass weighted velocities, right? So 2m comes with a v1 plus m comes with 0, then 2m plus m. So VCM will be 2m v1 over 3m, and it's going to be 2/3 v1. Okay, so I think you know how to do this thing. So this is going to be a magnitude of VCM is two-third V1. Now imagine a frame where VCM is fixed. So over here I'm going to write the I'm going to here draw the frame. So this is the center of mass frame. So VCM is fixed. That means both of this guy is coming and this guy is coming. And another property of the VCM is if you take a total mass, which is 2m, so P total momentum will be 2m plus m times VCM. I can illustrate that to you. So this is over here, you can see the total momentum initially, all x directions, so I'm not going to worry about x. It's going to be 2m times v1 plus m times 0. M times 0 is 2m v1. So now you can see that over here, just from VCM, you can say 3m times VCM is 2/3 v1. So this is 2m v1. And so this is actually a important property of the VCM. So if VCM is 0 in this frame, VCM will be, CM will always be there, right? For two particles in every frame. So in this frame, CM is the you fix, say, origin on it. So you just fixed origin, and the CM I can coincide the x to be the same direction as that. And so what you will see is this particle. If you're sitting there, you will see this particle coming with some momentum P1, and this other particle, of course, going to be you would say over there, but you will see because same momentum is going to strike it over here. So you have to have because CM is displaced. So you put it over here. Then you will see this guy will have also exactly opposite of this, particle 1 and particle 2, so that their total will be 0, because in the CM frame, P total equal to 0 in CM frame, because since VCM equal to 0 in CM frame, so P total, which should always be equal to M total VCM put in there, is going to be 0. So that's one of the characteristics of the center, and that's what things simplify. So you can see there's just one momentum, and because this is all momentum in the CM frame, so we have to do P01, P01. So we can say subscript 0 for quantities in CM frame. Okay, so over here, so this one will have some velocity v1, so I'm going to v01, and this will have some velocity v02. I actually wrote this too close. This is too far away, so the CM will still be is over here, P01 minus. So this will, not too close, is 2, and it's going to be V02 2. Of course, V02 P's are equal, the masses are different, so they will be momentum is the same in magnitude, direction the opposite, but the velocities will be different. So they will have to this will have a higher velocity to reach over here at the same time that this guy reaches over there in the CM frame. All right. So what is the relationship between the velocities here and the velocities there? That you can actually tell because you hop over there and then hop over here, right? So this V1, so relation between frame. So any vector, take any vector, any velocity vector. So V1 vector here, any of the velocities, okay? You can take V1 prime here. So V1 will be velocity of the CM. So hop in the CM, and then with respect to CM, whatever the velocity is. So like V01. Similarly for V2 will be VCM per velocity in the CM frame. And similarly after the collision. So after the collision will be V1 prime plus equals to VCM plus V01 prime. V2 prime equals to VCM plus V02 prime. So primes will be after. So this will be the relationship between the velocities. All right. So if we let's work out what's the initial velocity is. Okay. So I'm going to work out here V1 equals to VCM plus V01. So what is that guy? Okay. So what is this guy over here? This guy over here. Okay. So that guy over here is this, and say all along the x-axis. So along the x-axis, I'm going to work out. So V01 equals to V1 minus VCM. So V1 minus VCM, and so how fast is VCM going? So V1 minus VCM is going at 2/3 V1. So this is a vector relation between this vector, and this vector. So these three vectors, that's the relationship. And from there so this vector is still in the left frame. So left frame VCM. So this is going to be 1/3 V1. If you want to do, you can figure out V02 also. So similarly, V02 will be V2 minus VCM. So V02 is just minus the x components. So these are all like x components. And they're all positive over there. So 2/3 V1. So 0 minus 2/3 V1, so the minus 2/3 V1. So this is going at magnitude is 2/3 V1, and this guy's magnitude is 1/3 V1. Okay, so it's good to work these out this way, but our goal is to find this angle to be what will be maximum. And so this is, we need to look at the relationship of this guy and this guy and V01 prime afterwards. So what will be the V0 prime in here? Well, it's an elastic collision even in CM. So because elastic in CM, when the momentum comes in, is gonna have same. It's gonna return in some direction. Let's call it chi. Is going to return at some direction, but the value of this will be remain the same. P01 prime. Let me kind of erase this and draw a new picture here. So it's coming in P with a P01 and hits the other guy over here, and it's going to return with exactly P01 prime, which will be equal to P01. Magnitude will be same. Why? Because elastic kinetic energy is conserved. So kinetic energy of this particle be P01 square over 2 times its mass of M1. And kinetic energy afterwards will be P01 prime square over 2 times M1. So using these two, so elastic collision with kinetic energy, each particle will be preserved, and that will tell you P01 and P01 prime, they have to be equal. They're equal, which means velocity 01 prime in magnitude is equal to velocity 01 in magnitude. So velocity arrow here will be velocity was 1/3 v1 coming in, and it's going to come out some direction. We're calling it chi, 1/3 v1. And so here, so if I want to say something about this theta, there is a kind of a good way of looking at this vector. So this velocity is some, you can see v1 was fixed, so it is fixed, but I don't know which directions came out, and corresponding to 0 total momentum in this frame, the other particle will go exactly in the opposite direction. So this is particle 1 come out this way, particle 2 come out this way, and this will be some angle chi, and we need to figure out in which direction this will come out that makes this theta largest in the lab frame. And it turns out that we can actually answer by looking at this equation directly as in a vector diagram. There are other ways you can do it, but simplest one is to look at this equation, the relationship between this vector, and this vector directly in a vector diagram. Let me erase and get some clean place to work with. Okay. Okay, so we are going to draw out the vector. You have a say v1 vector, v1 prime vector. This vector equals to vcm vector plus v01 prime vector, with a vcm magnitude is 2/3 v1 and v01 prime magnitude is 1/3 v1. Okay, so this is the vcm 2/3. All right, and this guy's v01 0, 1 and some angle chi, which is kind of this size. Okay. So this is the VCM vector, and this is the V01 prime vector. So this from here to here will be the V1 prime vector, which will make this original direction. That's the horizontal direction, and this is the angle theta in this picture. Okay, we want to know when this will maximum. You can see that the length of this vector is 2/3 V1, and length of this vector is 1/3 V1, and V1 is fixed. So the only variable to find this maximum is what is the direction of what are the various direction this guy can go at 1/3. That will make this angle largest. So when we do it is just draw this out, all possible choices that you can have for V1 V01 prime vector, and this will be just a circle. Let me draw a circle. So it can be any direction, and you can see that some directions for this guy. So if you have this, then theta will be smaller. So the largest theta is when it's tangent. So when the V01 prime is in that direction, then the theta is the largest, theta max. So now we can isolate this triangle with this must be 90 degrees because this is radial, this is tangential. Tangential to this various directions V01 prime can take. And so this will be 1/3 V1, 2/3 V1, and this is 90 degrees, and this is a theta max. And this is some value V1, V1 prime, which we don't know yet. Okay, we can figure this out from here. So, but that's not part of the question. Question is asking find theta max, and this is just a right angle triangle. To sine theta max will be 1/3 V1 over 2/3 V1. So this just becomes a half, which means theta max is going to be 30 degrees, which is pi over 6. And so that's the answer. Yeah, so actually in the test situation, of course, you're not going to do all this explanation. You're going to go bang, 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 and you're just going to go through it. This is a little bit hard problem because you have to jump back and forth between two frames, and then you construct a actually vector diagram and to analyze this. So if you haven't seen this problem, probably there's not much time, or you can try to do brute force methods to try to get the maximum theta, but that will take you much longer. This is the shortest way of getting this problem solved. Okay, try to practice and see if you can tell other things in this setting. Try to practice going back and forth from this and CM frame. I think you should practice going back and forth. A good place you can go down is the website I have. I think I have a whole bunch of them. physicsbootcamp.org. Okay, I'll see you another video. Okay, bye.